Yes, sir.
Yeah. So in this session, we will continue the topic that we have started in the previous session, which is SVM. But in yesterday's class, we have discussed this SVM from the point of binary classification problem. So because SVM is essentially for the two-class classification problem. So in this session, we'll see how to extend it to the multi-class setting as well, right? So if time permits, we'll also try to discuss the decision trees also. We'll try to complete the two topics in today's session, okay? Because we may need break, I may need break, because some meetings are coming up in the coming days. So let us try to finish the two topics in today's session, if time permits, otherwise it's okay, right? So, chalo, let us start this session on the multi-class SVM. So, what is multi-class classification problem? All of us know about it, right? So, if there are more than two classes, we call that as a multi-class classification problem. It means input can belong to one of the k classes, where k is greater than 2, right? So, the prediction is, given a new input, we predict the class label from one of these k classes. So one of the k classes will be assigned as a label for the new instance, right? So each input belongs to exactly one class, not more, not less. Otherwise, we call the problem as a multi-label classification problem. So there is a difference between, please try to understand here, there are two terms. One is multi-class classification problem. The other one is the multi-label classification problem. So the difference is that multi-class classification problem, there is only one target value, target variable, right? In which each instance belongs to one of the k classes. Whereas in case of multi-label classification, we have multiple target values, variables. It means more than one output variable is present, then we call it as a multi-label classification or multi-label regression, depending on whether it is a classification problem or a regression problem, right? So if you are only interested in predicting one output variable, we call it as a single target classification, depending on whether there are two classes or more than two classes. Either it is a binary classification problem or a multi-class classification problem. If there are more than two target variables or the output variables, right? More than one target variables or the output variables, we call it as a multi-label classification problem. Okay. So in this session, our interest is multi-class classification problem, not multi-label classification problem. Okay. So do you understand the difference between multi-class and the multi-label classifications? Or should I repeat something? Anybody? Anybody?
Kindly repeat, sir. Just
Repeat, sir.
Okay. Your data looks something like this, right? X1, Y1, X2, Y2, so on, Xm, Ym, where Xi is the d-dimensional feature vector, Yi is the corresponding class label in classification problem. It's a discrete value. It means Yi belongs to one of the k classes. Am I right? Hello?
Yes, sir.
Right. So if k equal to 2, we call it as a binary classification problem. If k greater than 2, we call it as a multi-class classification problem. Fine? Till
Yes.
here it is clear, right? Yeah.
Yes.
Yes, sir.
So now instead of one target value, let's say you have multiple target values. Let's say yi is not a single variable, it's a vector, right? So it means you have one column of y's here, another column of y's, another target, right? So let's say that there is a image given to you. Okay. So image is containing multiple tags like there is a fish in the image, there is a water in the image, there is a tree in the image. Okay. So when you are representing the image, there is a feature vector to represent the characteristics of the image and the different labels. Label 1, let's say fish. Okay, present or not? Yes, it is present. Now it is labeled to water. Present or not? Yes, it is present. Label 3, tree. Present or not? Yes, it is present. There is another label. Let's say book. Present or not? It's not present. Okay. So multiple targets are there, right? Not just one target. So if you're interested in predicting multiple target values, then we call it as a multi-label classification problem, right? So in case of multi-class classification problem, you're just trying to make prediction for the one output variable. Whereas in case of multi-label classification problem, you're trying to make a prediction for the multiple output variables.
Okay.
Got it, right? Yeah.
Yes, sir. Sir, if this example kind of things are given, then it is clear, sir.
You just ask me if it is not clear to you. Please
Yes,
ask
yes.
me. I will give example. Don't worry
Now
about
it became very clear.
Yeah. Whenever you couldn't follow me, just raise it there and then so that I can clear the things. Okay. So don't keep it with you. I mean, don't hesitate to ask, and that will create a problem later. You will not be able to follow rest of the things. Yeah. Anyhow, in this session, we'll be focusing on the multi-class classification problem, not the multi-label classification problem. So understand the difference. Fine. So here are some of the applications of the multi-class classification problem. Handwritten character recognition. There are 26 characters. That means 26 classes. Object recognition, multiple, more than 2 objects are present, right? And handwritten digit recognition, news article prediction, which section of the news article should it belong to? It can be political news, cinema news, or crime news. More than 2 classes are there, right? So email, which folder should an email be placed into? More than 2 folders. So it is also an example of the multi-class classification problem. Like this, there are various other applications of multi-class classification problem. But SVM is essentially for the 2-class classification problem. So there are many approaches to handle the multiple classes using the binary SVMs, using the SVMs. One possibility is combining multiple binary classifiers. All these are the different ways to combine the multiple binary classifiers. Or there is another way also, training a single classifier using the multi-class optimization or the constraint classification. Okay, so it is slightly difficult for you to understand this at this stage. Okay, so we'll be focusing on this combining multiple binary classifiers. Okay, so the idea is very simple. Okay, you will enjoy this. Idea is very simple. Let me demonstrate the idea first, then we will discuss these 5 methods. Okay, so the idea is this. We are given a multi-class classification problem. Multi-class classification problem. Right, what we do is that we divide this into multiple binary classification problems. Given the multi-class classification problem, we divide it into multiple binary classification problems. Multiple binary classification problems. After dividing this, can we apply SVM on each of the binary classification problem?
Yes.
We can apply SVM. So apply SVM on all the binary classification problems, right? And combine the solutions for these binary classification problems to get a solution for the multi-class classification problem. Okay, so it is dividing the problem into multiple binary classification problems, solving them using SVM, combine the solutions to get a solution for the multi-class classification problem. That is the basic idea behind this, combining multiple binary classifiers. So the way, based on the way that we decide this multi-class classification problem into multiple binary classification problems, depending on the way that we decide this, we divide this, we have different techniques. One against all, one against one, decision tree structured SVM, binary tree structured SVM, error correcting codes, etc. Right? So this is depending on the way that we divide the multi-class classification problem into multiple binary classification problems. Okay. So now let us try to explore each one of these 5 techniques one by one. Okay. So I hope you are with me so far.
Yes,
Yes,
sir.
sir.
Yeah. So we'll start with this one against all classification. As the name itself is saying this, that one against all. It means we'll be learning this. One versus the rest of the classes. So suppose if there are four classes, so 1, 2, 3, 4. Let us enumerate them like this. So I'll learn one problem is creating one binary problem, 1 versus 2, 3, 4. It means I'll label this as a positive instance and I will label this as a negative instance, right? So it means all the instances that belong to class 1 will be labeled as a positive instances, and all the instances that belong to class 2, 3, 4 will be labeled as a negative instances. Now it is a binary classification problem and you can apply SVM. Similarly,
Yes.
2 versus 1, 3, 4, 3 versus 1, 2, 4, and 4 versus 1, 2, 3. So if there are 4 classes, you are learning 4 binary SVMs. So now tell me, if there are k classes, how many SVMs we need to train?
Sorry, K for K only, sir.
K SVMs, right? So the training complexity is order of k, right? Right. If there are k classes, all right. So this is the training part. So how to test it? How to assign a label for the new instance is the question. So given a new instance, we give it to all the classifiers. I give it to this and compute the score of W transpose Xi plus B, which is the line equation, W transpose Xi plus B. Give it to this equation, compute W transpose Xi plus B. Similarly, Wi transpose Xi plus B, compute Wi transpose Xi plus B. So given a new instance, I am giving it to each and every SVM and computing the score. Whichever the classifier maximizing the score, then I assign a label, I assign that corresponding class to the new instance. Like for example, if W2 transpose Xi plus B, if this is maximizing the score, I assign a label 2. If this SVM is maximizing the score, I assign a label 3. If this SVM is maximizing the score, then I assign a label 4 and so forth, right? So prediction is winner takes all. You pick up a class label that maximizes Wi transpose Xi plus B. It means whichever SVM maximizing this score, we take that corresponding class label for this new instance. All right. So is the idea clear? Everybody?
Yes, sir.
Yeah.
Yes.
So how many SVMs we are testing at the time of to classify a new instance? How many SVMs we are checking? K SVMs. We are giving it to all the SVMs, right? Yes. So the testing complexity is also order of K, 1 against all. Okay. So here is an idea. Learn multiple classifiers. Like there are 3 classes here. Each class is indicated with a different color. So we are learning a blue classifier that separates the blue instances from the rest of the instances. For simplicity, it is ignored, B is ignored here, bias is ignored, but you can take the bias as well. All right. So W transpose plus blue plus, W blue transpose X plus B blue. So greater than 0 for all the blue points. All right. Similarly here, you are learning the red classifier that separates the red instances from the rest of the instances. You are learning the green classifier that separates the green instances from the rest of the instances. So now you assign a label that maximizes the score. So given a new instance, give it to all these 3 weight vectors, compute Wi transpose Xi plus B, Bi and X plus Bi. So take a label that maximizes the score. So winner takes all. This is what is the idea and the visualization of it. Okay. So, but there are some problems with this approach. This approach may not work always. Like for example, you see these are the points that are not separable with any of the single classifiers. So the decomposition will not work for these kind of cases. Okay. So this is one problem. There are other issues as well. Let us see this. Okay. So one more problem is that there is no theoretical justification that why this method should work. There is no theoretical justification for why this method should work. We know the reason is this. You see that you are making these problems independent of one another. You are learning this model of this method independent of the model of this method. right? I mean, moral of this data, right? So learning the models independently. So because you're learning the models independently, there is no reason for them to be in the same numerical range. So if they're not in the same numerical range, it doesn't make any sense to compare them, isn't it? So because you're learning the problems independently, there is no reason for them to be in the same numerical range. So there are some calibration issues, right? There is no reason for them to be in the same numerical range, because if they are, suppose if they are not in the same numerical range, it doesn't make any sense to compare them, right? That is why there is no theoretical justification that why it should work, because these problems, these models we are learning independently, and we cannot provide any theoretical justification to support that they are in the same numerical range, right? Yet in many practical cases it works really well, right? So there is no theoretical justification, and there are some calibration issues, because we are comparing the scoring produced by the K classifiers trained independently. So there is no reason for the scores to be in the same numerical range. So it means that it might not always work, yet it works fairly well in many cases. Okay, so have you understood what is one against all classification, and what are the advantages and what are the disadvantages of this one against all classification? Is that clear? No? Should I repeat something? No response. What happened?
Anyway, when we are, every instance we are assessing theoretically only, no? So then why we are saying no theoretical justification?
See, madam, you are independently giving to the three different classifiers, right? See, when you are learning W of this problem, okay, so this problem, learning W, is independent of learning W from this problem,
Yes.
right? So when you are learning them independently, can you say that they will be in the same numerical range, this W and this W?
No.
Not possible, right? I
They
mean,
won't.
at least we
Yes.
cannot give any theoretical justification that they will be in the same numerical range. Maybe they will be in the same numerical range, may not be. We can't guarantee it, right? We can't provide any theoretical justification that no, they will be in the same numerical range. We can't justify it, right? That's what it is saying.
Okay, sir.
Got it, madam? Clear?
Yes, sir.
Yeah. Everybody else, is it clear? Is the idea clear? One against all?
Yes, sir.
Yeah.
Yes, sir.
So let me summarize here. What is the training complexity? How many SVMs are you training? In terms of number of SVMs, I'm asking the complexity.
K.
How many? Order of K. And what is the testing?
Order of K.
Order of K. So the next one is 1 against 1. From the name, can you guess what it is? 1 against 1. It means between every pair of classes, we are learning a classifier or SVM, right? Suppose if there are 4 classes, 1, 2, 3, 4. What are the possible pairs? 1 versus 2, 1 versus 3, 1 versus 4, 2 versus 3.
16, sir.
Madam?
16 pairs.
6 pairs, not 16. 6, right? 4C2, 6. No, see, madam, you took 4 times 4, is it?
Yes, sir.
See, 1 versus 2 or 2 versus 1 are the same or not? Do we have to do it 2 times?
No, sir.
Not required, right? So half of them will go. And one more thing, 2 versus 2 or 1 versus 1, do we have to do? We need not do them also, right? Madam, 2 versus 2, 3 versus 3, 4 versus 4, all these are not required, right?
Two unique, but
Yeah.
is considered as one.
So 2 versus 4 and 3 versus 4. So total 6 classifiers we need to train. So if there are four classes, we are training 6 SVMs. If there are k classes, then it is kc2. It means k into k minus 1 by 2. These many combinations we will get. Okay. So assumption here is that every pair of classes is linear, is separable, right? And for every pair of classes j and k, we create a binary classifiers by taking all the labels, all the examples with label j as a positive and all the examples with label k as a negative, right? And we train a binary SVM. Okay. So how many classifiers we are training here? How many SVMs we are training?
6.
6. If there are k, then k into k minus 1 by 2, which is
Yes.
order of k square, right? Right. So the training complexity is order of k square, right? And now training part is over. How to classify a new instance is the question. How to classify a new instance is the question, right? So given a new instance, we give it to all the classifiers. We give it to all the classifiers and take the majority voting. Okay. So I give it to this classifier. Let's say it is classifying it as a class 1. So class 1 has got 1 vote so far. I give it to this classifier, right? I give it to this classifier. Let's say it is classifying it as 3. So class 3 has got another 1 vote, right? I give it to this classifier. Let's say it is classifying it as 4. So class 4 has got 1 vote so far. I give it to this classifier. Let's say it is classifying it as 2. So class 2 has got 1 vote now. I give it to this classifier. Let's say it is classifying it as 4. Class 4 has got 1 more vote plus 1. I give it to this classifier. Let's say it is classifying it as 4 again. So I've got another vote. So this is 3 votes for class 4, 1 vote each for class 1, class 2, class 3. So which label should be assigned?
Class 4.
Class 4. The label with the more number of words we assign, right? So class with the most of the words is the winner. This is the prediction. So tell me how many classifiers we are checking to classify a new instance?
K square only.
K into K
Yes,
minus
k
1 by
into
2.
k minus 1 by 2, which is order of k square, right? Both the training and testing complexities are order of k square, order of k square. So if you compare it with 1 against all, 1 against all is training complexity, order of k, testing complexity is also order of k, right? Whereas 1 against all, the training complexity and testing complexity, both are order of k square, right? So here, every pair of label is linearly separable. That's what the assumption is that. And when the pair of labels is considered, all the others are ignored. So based on this, can you tell me that are we considering the whole data set whenever you are training a single classifier? Are you considering whole data set or part of the data set when you are training a single classifier? Let's take this 1 versus 2. Are you considering whole data set? You're considering the instances from class 1 and class 2 only, right? You're ignoring rest of the instances. Am I right?
Yes.
Right. Similarly, when the pair of labels is considered, you are only considering instances from those 2 classes, ignoring rest of the instances. It means at any point of time, you are considering only part of the data set for the training. It means there is a chance that the training data is smaller. What happens if the training data is smaller? There is a possibility of overfitting, right? So that issue is there with this. So problems are order of k square weight vectors to train and store, which is more when, especially when k value is huge, and size of the training set for a pair of labels could be very small, that may lead to the overfitting. Another problem is that what if the 2 classes get the same number of votes? Again, there is a uncertainty, right? Prediction might be unstable sometimes if you use some random tie breaking rules, right? So these are the problems with 1 against 1. Okay. So if you compare the complexity so far, 1 against all, training complexity, testing complexity, training complexity, testing complexity, 1 against 1. This is order of k, this is order of k, and 1 against 1, order of k square and order of k square. Okay, so the testing complexity is also high for this 1 against 1, right? And there is a possibility of overfitting because it is not considering the whole training data, only part of the data. That means it is only considering some small data that may lead to overfitting problem. So the next one is directed acyclic graph SVM, DAG SVM we call it as. So before we're going to discuss that, is these two ideas clear to you? 1 against all and 1 against 1?
Yes, sir.
Okay. So now we'll see the DAG SVM. In the DAG SVM, training is same as 1 against 1. It means DAG SVM is also training between every pair of classes.
Sir, we have not.
I've not yet gone to that slide. I'm just explaining. Okay, no problem. Now it is in the slide. So the training is same as 1 against 1. That means DAG SVM is also training between every pair of classes. Every pair of classes. So what is the training complexity if it is same as OAO for DAG SVM?
Order
This is
of
also
k square.
order of k square, k into k minus 1 by 2 number of SVMs it has to train. So this is training is order of k square. So now how to test a new instance, how to check or how to make a prediction for the new instance. So the advantage of this DAG SVM is that it arranges these binary classifiers in a certain fashion so that it reduces the testing complexity. So it arranges them in a directed acyclic graph like fashion as you see in this figure. Okay, so I'll tell you how to construct this DAG SVM. So let's say that there are 5 classes, 1, 2, 3, 4, 5. So take the two extreme classes. The extreme classes are 1 and 5. So keep this in the root node, 1 versus 5. This is in the root node. As you move towards the left side, decrease the right side number by 1. As you move towards the left side, decrease the right side number by 1. It means 5 is reduced to 4, 4 is reduced to 3, 3 is reduced to 2. Right? Similarly, as you move towards the right side, increase the left side number by 1. So 1 is increased to 2, 2 is increased to 3, 3 is increased to 4. Repeat the same process for all the internal nodes as well. Right? So if you get the same classification, like for example, you see that the right node of this is 2 versus 4, left node of this is 2 versus 4, right? Don't create two separate nodes, take them, let the pointers pointing to the same class, same node, right? So this is how we construct this directed acyclic graph. I'll repeat if it is any confusion. Initially, we are taking the two extreme classes and keeping the classification corresponding to that in the root node. So the two extreme classes are 1 and 5, 1 versus 5, we are keeping it in the root node. As you move towards the left node, left side, decrease the right side number by 1. It means 5 is reduced to 4, 4 is reduced to 3, 3 is reduced to 2. Similarly, when you move towards the right side, increase the left side number by 1. 1 is increased to 2, 2 is increased to 3, 3 is increased to 4. Right? So this process we are repeatedly doing it for all the internal nodes as well. Right? Understood how to construct this DAG?
Yes, sir.
Right. So now to classify a new instance, we give it to the root node. So it is taking a decision of 1 versus 5. Suppose if it is classifying it as a 1, what is that it means? It is also saying that it is not 5. Am I right? When it is saying it is 1, it also means that it is not 5. Am I right? When I give a new instance to this 1 versus 5, let's say that classification that it is giving is 1. What is that it means? Can we interpret it as a not 5? If it is
Yes.
classifying it as a 1, we can interpret it as a not 5. Isn't it? Equivalently, it is not 5. When the classifier output is 1, on the other hand, it is also saying that it is not 5. Hello, everybody. Am I right?
Yes, sir.
It's also saying that it's not 5. It means All the combinations with 5 can be ignored in the subsequent check. So you need not check them further. So come to the left side and give it to this classifier. So let's say it is classifying it as a 4. What is that it means? It is also saying that it is not 1. So all the combinations with 1 can be ignored in the subsequent check. Come here. Let's say that it is giving to 2 versus 4 here, right? So let's say it is classifying it as a 2. It means it is also saying that it is not 4. All the combinations with 4 can be ignored in the subsequent check. And come here and check 2 versus 3. It will classify it as either 2 or 3, one of the 2 classes. So finally, one label it is assigning. Observe this carefully and tell me how many classifiers we are checking if there are 5 classes. How many classifiers we are checking to classify a new instance? 1, 2, 3, and 4.
7.
Four.
4. Oh no.
Only 4 we are checking, right? We are giving it to this, letter this, letter this, letter this. 4. So if there are k classes, how many classifiers we need to check at the time of testing?
K into K minus 1 by 2.
No, that is
K
training.
minus 1. Acha, testing it's K minus 1.
K minus 1. K minus 1 is order of k, right?
Yes.
The training complexity is order of k squared and the testing complexity
Testing
is
order of K.
order of k. Can you compare it with OAO? OAO is what? Training
It was
complexity?
order of k square only.
Order of k square, order of k square. Can you compare it with OAA?
Order of K and order of K.
Order of k and order of k. Right? So the testing complexity it is reducing, the training complexity is still the same, order of k square. So let us have a look at the next method, which is binary tree structured SVM. So it arranges these classifiers in a binary tree like fashion, right? So every time it divides all the classes into two disjoint groups and learn a classifier between them. Like for example here, if there are 5 classes, the root node, we are learning a binary classifier between 2 groups, 1, 2 versus 3, 4, 5. So we're learning a binary classifier between them. So anything that will be classified as a negative will be coming to 1, 2. Anything that will be classified as a positive will be coming to +1, or the other way also, 3, 4, 5. So now to make a further decision of whether it belongs to 1 or 2, you can learn a classifier between 1 and 2. Similarly here 3, 4 versus 5. And to take a decision between 3 and 4, you can learn another classifier between 3 and 4, right? So just for the sake of understanding, we made the groups based on the enumeration of the classes, but usually we don't do that, not based on the enumeration. There are other ways of grouping the classes that we will see later. So to understand it better, let us take 8 classes, right? 8 classes. So you can initially have a classifier between 1, 2, 3, 4 versus 5, 6, 7, 8. And here, after this, you can have a classifier between 1, 2 versus 3, 4. This side, you can have a classifier between 5, 6 versus 7, 8. And this side, you can have a classifier between 1 versus 2 and 3 versus 4. And here, you can have a classifier between 5 versus 6, between 7 versus 8. All right. Say this side, you can have a 1 or 2, 3 or 4, 5 or 6, 7 or 8, right? So look at this carefully and tell me how many classifiers are we training if there are 8 classes? How many classifiers are we training if there are 8 classes?
Sir, 6.
6 or 7?
Sir,
4 plus 2 plus 1. Total 7, right?
yes.
Yes, sir.
So if there are 8 classes, you are training 7 SVMs. If there are k classes,
K minus 1.
k minus 1, which is order of k. So the training complexity is order of k. So how to test? How to classify a new instance? So given a new instance, I give it to this classifier, root node. It will either classify it as a 1, 2, 3, 4 or 5, 6, 7, 8. If suppose if it is classifying it as a 1, 2, 3, 4, right? Come to the left side and give it to this classifier. It will either classify it as a 1, 2 or 3, 4. Suppose if it is classifying it as a 1, 2, again come to the left node and give it to this 1 versus 2. It will either classify it as a 1 or 2. So tell me how many classifiers we are checking to classify a new instance.
K by 2.
K
Order of
is 8. How many are we checking?
3.
K by 2 minus
3,
1.
right?
Log of k. Every time we are having it, we are discarding the other
Log k
half.
base 2, right? So basically, the number of SVMs that you are checking is equivalent to the height of the tree.
Yes.
If it is a balanced binary tree, what is the height of the tree? Log k base 2,
Log
right?
k. Yeah.
Log k base 2. So the number of SVMs that you are checking at the time of testing is order of log k base 2, which is much better as compared to the previous, right? Right.
Yes, sir.
So here I mentioned one term here. I said balanced binary tree. What if it is not balanced binary tree? Then in the worst case, you will have to check order of k, right? If it is always imbalanced, like 1 versus 2, 3, 4, 5, 6, 7, 8, then here again 2 versus 3, 4, 5, 6, 7, 8. So suppose if the grouping is like this, that's the worst case grouping. Then we may have to check order of k number of SVMs in the worst case. But average case and the best case, it is order of log k base 2. And one more thing I have mentioned here. Here I have done the grouping based on the enumeration, right? Based on the numbers, right? To make you understand. But usually the grouping is not based on the numbers or the class number or the enumeration of the classes, right? Grouping is based on the similarity between the classes. It means we group all the similar classes into one group. Okay, in other words, we are making them into two disjoint groups such that all the classes in one group similar to one another, and classes from the two different groups are dissimilar to one another. Got it, right? Hello?
Yes, sir.
Right. So every
Yes, sir.
time we
So
are
generally we
recursively,
do, so 1 second. Generally we see point-wise similarity, group-wise similarity also can be checked.
you can check.
So did we
Sir, I mean, in fact, there are multiple ways of doing this grouping. You can just consider the features, you can just consider the class labels, and there are hybrid approaches also.
Okay.
So this process, we call it as a binarization. Binarization is what? Recursively dividing these classes into two disjoint groups, right? So this is what is the binarization. And binarization is done based on the similarity between the classes. So making them two disjoint groups such that all the points belong to one group are similar to one another, and points from the two different classes are dissimilar to one another. So you can apply the clustering techniques also here to make them into two disjoint groups. Okay, so here is a hierarchical multi-class model, binary tree structured, seems to the best option so far, because the performance wise, you see, performance of all these methods is more or less same. Only the different terms of the training and testing complexities. So far, it is the most efficient one, right? Order of log k base 2, right? We haven't got that much less for the previous approaches, right? So far it is the best option, but only problem is the critical decision of binarization, right? And prediction is dramatically fast. So what is binarization? As I have mentioned to you, binarization is recursively dividing the classes into two disjoint groups in every node of the tree and training SVM at that node. Okay, so there are many ways to divide k classes into two groups. Okay, So to have a proper grouping of the, many ways of dividing k classes into two groups. Okay. So like the divide based on the k, based on the class labels, divide based on the feature vectors, or some of them are the hybrid approaches, right? There is some research going on here also. Even we had some 2-3 papers in this on this binarization. Not now, long back, some 4-5 years back.
Your paper, sir.
Yeah, my papers. Yeah, so challenge is optimal binarization. So strengths of this include training and testing complexity, early termination, discriminating order, optimal discriminating order, and stage-wise linear separability. These two you may not understand right now. I have an example for this to show to you. I will show it in the coming slides. So what do we mean by optimal discriminating order and the stage-wise linear separability? Both of them are relevant points only. So we see that. Weakness is it is a suboptimal two-stage procedure in a sense that binarization step is different from the model building step, right? Right. So because you are adding an additional step of binarization after dividing them into groups, again you are separate. You are learning a classifier between them, right? So it is a two-stage procedure. Tree construction is different from the classifier learning, right? All right. So here we'll see these 2 points: discriminating order.
One second, sir. This slide we want to digest this 1 second.
Madam, it's simple. It's two-stage procedure only, right? First, we identify who are the similar classes and making them into two groups, and then learning a classifier between the two groups. So trees building is different from the classifier learning. Tree construction is different from the classifier learning, isn't it?
Yes. Okay.
Yes. Yeah. So what do we mean by optimal discriminating order and the stage-wise linear separability? Let us see an example. Here is an example of 4 classes, 1, 2, 3, 4, let's say, right? So if you see this, is it a linear? Is there a linear separation between 1 versus 2, 3, 4?
No, sir.
No. 2 versus 1, 3, 4? No, right? Or
No.
2 versus 3?
No, sir.
2 versus 3, there is, okay, you consider only 2 and 3. Okay, but anyhow, so yes, so there is not linearly separable, right? Right. But if you see this, 1, 2 is linearly separable from 3, 4. Right? Stage-wise linear separability is there. So if you could identify the optimal discriminating order, right? What are the things that we have to consider at the root node? What are the things that we have to consider at next internal nodes? If you have that optimal discriminating order, then it is linearly separable. Like you see this, 1, 2 is linearly separable from 3, 4. 1 is given 1 and 2, 1 is linearly separable from 2. Given 3, 4, 3 is linearly separable from 4. So there is a stage-wise linear separability, and only the binary tree structured SVM has that flexibility to do this. Other methods doesn't have this flexibility. Like you see this 1 against all. Is it possible? No, right? It's not possible to get that optimal discriminating order in any of the other methods. That is possible in the binary tree structure SVM. Similarly here, 1, 2, 3, 4, let's say. 1, 3 is linearly separable from 2, 4. Right? And given 1, 3, 1 is linearly separable from 3. Given 3, 2, 4, 2 is linearly separable from 4. Right? So this is also optimal discriminating order, and this can be done using this. That is another advantage of this binary tree structured SVM. I hope these 2 points are clear. Clear? Shall we move on? Yes. Yeah. Okay. So the next idea is error correcting output codes. Before, Acha, let us summarize the complexities no, so far. Do you remember? What are the methods that we have discussed so far?
Yes, sir.
OAA, OAO,
OAO
tag,
and tag.
binary tree structured SVM. Training complexity and testing complexity. Tell me, OAA.
Order of K. Order of K.
OAO.
K square,
K
Order
square
K
and K
square,
square.
K square,
K square.
Yeah.
Sir, order of K square and order of K.
K minus.
Binary tree SVM.
Yes.
Order of K.
Order of log K.
Log
Order of log K.
Two.
log.
So far, binary tree SVM seems to be the best option, right? Yeah. So
Sir,
let us go to the next idea. Before I demonstrate the next idea, I want you to answer one question. Suppose if I ask you to represent 8 numbers in a binary format, 0 to 7, how many bits do you require?
4, sir.
3 bits.
3 bits are enough, right?
Mhm.
0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, so on, 1, 1, 1. Right? Suppose if I ask you to encode 8 classes C0 to C7, right, into binary strings so that each and every string is unique, what are the minimum number of bits that you need to encode them into binary strings? 3?
4 bits.
3.
3, right? C0,
Oh, so
C1,
eight classes. Okay,
8
sir.
classes, C0 to C7, right?
Mhm.
I can encode C0 as a 0, 0, 0. I can C1. Everyone is unique from the other one, right? Right. So now, agree till this point? So let me write it this way. C0 is 0, 0, 0. C1 is 0, 0, 1. So on. C7 is 1, 1. Now the data given to you looks something like this. Let's say there are 8 classes in the data. X1, Y1, X2, Y2, so on X and Yn. And yi can be one of this, belongs to one of these 8 classes, C0 to C7. Let y1 is some C1, y2 is some C0, and so on, yn is some C3. Okay, so can I encode C1 as 001? Can I encode C0 as 000? So on, how to encode C3? Not necessarily this way, you just have to take the unique strings, that's all. Okay, C3, 0, 1, 1.
1, 1.
Okay, so now let me take this as the feature vectors. Instead of taking this as a target value, I'll be taking this as a target value, the first bit of this encoding string. This as the input vector and this as a target value. Isn't it a binary classification problem? Hello, isn't it a binary classification problem? Can I try an SVM?
Yes, sir.
Right. I try an SVM 1. Now this time I'll be taking this as a input vector. Now the second time I'll be taking second bit as a input vector, output value. Can I try another SVM?
Yes, sir.
SVM2, I'm taking this time. Training SVM. Now same input vectors are same. This time I'm taking the third bit as the output variable. This is also binary classification problem. Can I try SVM? SVM3. So if there are 8 classes, how many SVM you are training?
3.
3 SVMs.
3.
If there are K classes,
Sorry.
log K base 2. How many bits do you require? How many to represent that, to encode that as a binary string? If there are K classes, you need log K base
Log
2 number
K.
of bits.
Huh.
Yeah. Log K base 2. It means the number of SVMs that you are training is order of log K base 2. Okay. So training is order of log K base 2. Order of log K base 2. So far it is the best, right? You see this. Binary tree also order of K. Training complexity. This is order of log K base 2 only. Right? Now, how to classify a new instance? To classify a new instance, I give it to SVM1. Let's say it is classifying it as 0. I give it to SVM2. Let's say it is classifying it as a 1. I give it to SVM3. Let us say it is classifying it as a 0. This is the prediction string that we have got. We have to decode it. So if I decode it, what is the class label corresponding to this? Class
C2. C2.
we assign a label class 2 to this. Okay. So how many SVMs are you checking to classify a new instance? 1, 2, 3. In this case, so if there are k classes, how many SVMs? Log k
Log
base.
K.
So the testing complexity is also
Log K.
order of log k best. Okay. So let me write it here. ECOC. Where should I write ECOC? What is the testing complexity? Training complexity, order of log k base 2. Testing complexity, order of log k base 2. But what is the problem with this method? There is one problem with this method. What is the problem? Even if one of the classifier makes a mistake, yes, madam, please.
Yes, yes, sir. No, no, go ahead.
Yeah, even if one of the classifier makes a mistake, the whole thing goes wrong. Am I right? Even if one of the classifier makes a mistake, let's say by instead of making it as 0, it is predicting it as a 1. The whole interpretation will go wrong. Now it will become class 6. Isn't it? Hello? Isn't it?
Yes,
Even
sir.
if, so even if one of the classifier makes a mistake, final prediction is wrong. This is the problem with this method. So to avoid this problem, what we do is that we add a error correcting bits. That is why it is ECOC SVM. Error correcting bits. Error correcting bits are the additional bits that we are adding randomly. So in addition to these 3 bits, we are adding 2 more bits. 2 more is some constant. 2 means constant, right? It means like that you can add also 3, you can add 4, depending on, right? So you are adding some constant number of bits randomly. By following uniform distribution, you can generate zeros and ones randomly, add 2 columns, right? So now try and find, see, now 0 is encoded as 0000000. 1 is encoded as this, and so on. 7 is encoded as this. Okay. All right. So now we train 5 SVMs. With the first bit, we train SVM1, SVM1. With the second bit, we train SVM2, and so on, SVM5. Given a new instance, I give it to all the SVMs, right? And let the encoding string is 11010. Okay, 11010. Okay, it's not possible to get exactly the same string.
Assign the values with each label
Right?
string.
Ah,
Oh shit.
Geeta ma'am, what happened?
No, I did not keep it unmute, sir. Sorry, muted, and I was just reading it.
Okay, no problem. Yes, so let the prediction string is 11010. Hey, when you give a new instance, let's say the SVM1 is predicting is a 1, SVM2 1, SVM3 0, SVM4 1, SVM5 0. Now see that which one of these prediction strings, which one of these encoding strings are more close to the prediction string. So check with this one, how many bits are different? Compare this with this. How many bits are different? What is the Hamming distance between them? 3. 3 bits are different, right? These are all zeros. Here there are 3 ones. 3 bits are different. Am I right? Hello.
Yes, sir.
Yeah. So what is, how many bits are different in this case? This is also 3, I
Sir.
guess. 1, 1. First 2 are different. 0. First 3 are different, right? So 3 bits.
Yes, sir.
Compare it with this.
Sir, 2.
2. This.
4.
This one. 2.
2.
This one.
3.
Yeah. 1, 3. Yeah.
Yes, sir.
This one,
1,
1.
2.
So which is more closer? Which?
Sir, 4.
6, right? Distance. This is the distance, right? Distance less means it is more
Shorter
closer.
the distance.
Yeah. So 6 is lesser distance. It means this is more close, right? You assign a label 6. So the closest label to this is 6 with a code word of 11000. Right? This is how we assign. So we assign label 6. Have you understood the procedure? We'll analyze the complexity. Have you understood the procedure?
So here you have written in orange, longer the code length is better. Achha, for that. Okay, okay.
Like code length, this is 5 code length, right? So if you have one more, like 6 code length, that is better than this. It means you will get a more stable one, right?
Yes, yes.
Yes. Okay, so what is the complexity of this? You're just adding some constant number of bits, right? It means encoding string length is log k base 2 plus some constant number of bits. So these many number of SVMs you are training. So order of log k base 2 plus some constant. Isn't it order of log k base 2? Who is good at algorithms? You should confirm. Plus constant number means you can ignore the constant term, right? In the complexity analysis. So order of log k base 2, both the training and testing complexities, because you're just adding the constant number of bits. Clear? Hello? Clear?
Yes.
Yes.
Sir, in the earlier slide, yes, sir. Sir, how did you decide that the coding format, how did you decide this coding format? First
Coding
one
format.
is 000, second one is 00110. The next.
This is first 3 bits are normal encodings, madam. Binary encodings. 0 is encoded as 00. All this till here it is normal encoding only. That
Yes,
whatever.
yes.
These are randomly generated bit, madam.
Okay, sir. Okay.
By following, it means, let's say I have to generate this bit. Randomly pick 0 or 1. So it is randomly picked as 0. Can be equivalently 1 also. We don't know what it is. Okay.
Oh, yes, sir. Okay,
Right.
sir. Okay.
Because they're randomly generated.
Okay.
These 2 columns are randomly generated.
Okay, sir. Okay.
So that's all about this topic. Thank you very much and happy learning.
Sir,
But
So superb.
what are the sir?
sir,
Hello.
Parmesha sir.
What are the real world applications? Where exactly this SVM is being used?
Lots of
And
applications, sir. Wherever you have the classification
no,
application.
any circumstance, any specialized, because some of the classifier they are meant for very good in this particular domain. And all. Is there anything about SVM? Where can we use SVM?
Specifically, I cannot tell you because first of all, that we cannot say a particular classifier is work best for a particular situation in all the conditions. Okay, I mean particular application in all the conditions, right? So it depends on various other things as well, not just the application. It depends on the data set at hand. It depends on the size of the data set at hand. It depends on the number of features. It depends on the lot of things. So you cannot say one particular one particular method works best in every situation. That is true. Given an application also, we cannot say that this particular method works better for this application, because there are a lot of other things that are different. Okay, so we cannot judge that, we cannot also conclude that this method is working well in this particular application, in all the situations. Maybe in particular situation that may be working well, that we cannot generalize and say that this suits well for this particular application in all the conditions. Got it, sir? Not only me, anybody cannot tell that.
Okay, sir.
Yeah.
Understood. Thank you.
Hello, sir.
Yeah.
Sir, I'm still stuck up with that. Can we use one hot encoding for that? What you did, no?
What I did?
The second last slide. The second last slide. Here. One hot encoding will do. I mean,
One
how
hot
many?
encoding will be too much, right? You will have to add 7 bits. And you know, there is
7
another
bits.
problem. 8 bits. 8 classes are there. There is one more problem with that. Tell me what is the problem? Class imbalance problem will be there, na? Because in any column, only one, rest of them are zeros.
Yes.
Isn't it?
Yes.
So I mean, only one class is encoded as 1, rest of the classes as 0.
Yes.
So it means there many instances will be zeros, very few instances will be ones. Class imbalance problem would be there.
Okay. Okay, sir. Okay, sir.
2 problems. Yes. All right. That's all. Any other query? So let me demonstrate this Jupyter notebook. After that, if we have time, we will proceed with the decision trees. I don't think it is already 7:10. By the time we finish the demonstration, it will be 7:30. Decision tree requires around 1 hour to 1 hour 15 minutes to complete the theory part. But up to you. If you want to, if you can spend time, I can continue. Similar. I mean,
Once again, yesterday when we were seeing binary SVM, we have taken a lot of care for error and all. That care we need to take for multi-class SVM as well, right?
lot of care for error means?
To loss related, sir.
Yes. Here also you are doing SVMs only. But on top of this, there is another procedure implemented to divide the multi-class problem into multiple binary classification problems. So for to solving each binary classification problem, again you are using that SVM only. Got it, madam? On top of this, you are doing this. This procedure of 1 against all, 1 against 1 is on top of that.
Yes.
All right. So 6-step process. Tell me 6 steps. Import all the required libraries. Next.
Processing.
Load the data set.
Loading the data.
Prepare
the data set. Split the data set. Build the model. Predict and evaluate. Simple. Okay. So only the method varies. So we just have to see that how to use that method. That's all. Rest of the things are same. Right. So here are the libraries that I've imported. So I'm just importing this model selection, train test split, pandas, numpy. This is for some data loading and some calculations if I want to do numpy. This is support vector classifier. I'm importing from sklearn.svm. And these are the evaluation metrics. Right, you can also import accuracy score. Just to show you the different options, I've imported classification report and confusion matrix. Right. So these are the libraries that I am importing. Now the second step is loading the dataset that I am reading it from the local database. Diabetes dataset. This is a disease diagnosis example that we have promised in the browser also. Right, disease diagnosis. Classifying predicting whether the patient has a diabetes or not. Okay. Similarly, you can do it for the cancer diagnosis also if you have the data set. There are data sets also for cancer diagnosis. You can do that. So this is a diabetes data set and this is how it looks like. These are the features: number of pregnancies, glucose level, blood pressure, insulin level, BMI, diabetic predictory function, age. Outcome is either patient has a cancer or not, 1 or 0. Okay. Right. This is how the data looks like. Right. So far clear, right? 2 steps.
Yes, sir.
Third step is prepare the data set in the required format. Drop the last column, outcome column. Remaining things will be X. Just access the last column. This will be Y. This is the preparation of the data set in terms of X and Y. Next is splitting the data set into training and testing. We divided the data set into training and testing, right? Test size is 0.3. If you want, you can fix the random state. If you don't fix, each one of us will get different results. Don't worry about that. Okay. But you can do the cross-val score also that I have shown you at the very beginning. Split the data set, training and testing. Now build the model, right? So SVC, kernel is linear kernel. If you want to build linear SVM. So by default, kernel is RBF kernel. So if you want to change the kernel, you have to explicitly specify this. If you don't specify anything here, if you directly call SVC like this, by default, it will take it as a RBF kernel, right? So I'm building the linear kernel first, linear SVM first. So I specified linear kernel as a linear. There are other methods also to implement linear SVC also there that we're gonna see coming. Okay. So model.fit and then fit for the training data and then predict for the test data. So model.predict on the X test. So I'm printing the classification report and the confusion matrix. So in the classification report, we'll have the methods, measures like precision, recall, F1 score, etc. And in the confusion matrix, it prints the confusion between the different classes, right? So you see this. There are 2 classes. Diagonal elements are the correct predictions. 127 class 0 instances are classified as class 0 only. 43 class 1 instances classified as class 1 only. But here 19 is misclassifications. 19 of the class 1 instances are misclassified as class 0. Similarly here, this is 42. 42 is also misclassification. 42 of the class 0 instances are misclassified as class 1. Right? This is the confusion matrix, confusion between the different classes. Alright. The next one is the kernel one. I mean, directly calling SVC, it means it is by default taking it as a RBF kernel. Same model.fit, model.predict, confusion matrix and classification report for the same data. Right. So this is the results. All right. So like this, you can check any other kernels as well. All right. So here I've shown you the different one to show you the multi-class classification problem. Are you with me so far? Following, right?
Yes,
I'm
sir.
not.
Yes,
Yeah.
sir.
Yeah. So this is the
Sir,
yeah, madam.
binary classification, what we did is, so just to take the slide little up, I mean this screen, down. Yes, stop, sir. So this, it means 130 patients were identified to be the diabetic, correctly classified.
No, 133 no diabetics. Actually,
No,
also they don't
sorry,
have direct.
ulta.
Not, yeah, class 0. 133 class 0 instances are classified as class 0 only. It means all
Okay.
of them are correct classifications.
Right.
And 37 class 1 instances are classified as class 1. It means diagonal elements are the correct classifications, madam. All the diagonal numbers are the incorrect classifications.
Okay. Sir.
So this is the, what is that called? I forgot. IRIS dataset. You have, you know the IRIS dataset, right? We have discussed
sir.
it also. One of these classes. It's a flower dataset. There are 3 kinds of flowers. I mean 3 classes and 4 features: sepal length, sepal width, petal length, petal width. So this is also an example how to read a dataset from some URL. So the dataset is present at this URL. You can check also by typing this URL in the search bar. These are the column names that we are explicitly specifying, because in the data set column heads are not given. That's why we are specifying explicitly column names. So we use the same read CSV. Instead of passing the file path, you just pass this URL, right? And names, give the names as this column names. This is how the data looks like. Sepal length, sepal width, petal length, petal width, and this is the class label, right? So yeah, so this is the data set. Now prepare the data set in the required format. Just drop the last column, remaining columns will be X. Just access the last column, that will be Y. Split the data set. So now this time you are calling the polynomial kernel SVC. Degree is 4, right? It's a polynomial kernel. You need to specify additional parameter. What is the degree of the polynomial? You're specifying it as a 4 here. It's a multi-class classification function. You can explicitly specify decision function's shape. Whether it is 1 versus 1 or 1 versus all, like that you can specify. Different options are there. If you don't give anything in the decision function shape, by default it will take it as a 1 versus all, OVA, right? So here you are modifying it, OVO you are taking, it means 1 versus all, 1 versus 1, sorry, 1 versus 1. Similarly, you can take the other decision functions also, you can specify. Model.fit, model.predict. Okay, classification report and confusion matrix. All right, clear, right? This is all correctly classified in this example. Okay, but you can try multiple times. Clear, right? So far, or should I repeat anything? Nobody is replying.
Sir, how do we decide the degree of polynomial?
That is the hyperparameter to tune, madam.
Do we get that from some calculations?
So
No, no,
can we apply grid search here to find out the best degree?
You can do that, but grid search means what? If you have multiple parameter combinations, you can, grid search is helpful. Otherwise, it's one dimensional only, right? Degree 1, degree 2, degree 3, like that. Yes, you can do grid search. I mean, you were asking, can I apply that method directly? You can do that.
Sir,
So that I can assess for degree 1 how much I'm getting, degree 2 how much, then I can.
Yes, 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 you
Judgment.
can do that.
Sir.
Sir, tell me.
Sir, what about the kernel trick? I mean, I'm interested in that. Like, why the similarity matters? Because can we have our own similarity between vectors? Like in case of strings, can we have our own similarity functions? Like how what is your take on that kernel trick? Just briefly explain.
Sir, see,
Any-
this kernel trick is like, the idea is very simple. What are you doing in the given set of, or in the original space, the data is not linearly separable. What are you doing? You are applying kernel trick and transforming the problem to a different space where there exists a linear separation between them. Okay, and what kind of transformation you are applying is decided by what kind of kernel that you are applying. It means what kind of features that you are generating is decided by the kernel function. So if you apply polynomial kernel, you get one set of features. If you apply RBF kernel, their function that you are applying is different. Therefore, you get a different set of features. Similarly, other kernels, what depends on what kind of kernel that you are applying, right? The transformation that you are making to the data decided by the kernel function. So the original X given to some function, right, kernel function, and it is transforming the input space. And when you transform the input space, there exists a linear separation between them so that you can apply SVM. So transforming the problem, you're not changing the solution. Please see that.
Okay.
Sir, actually this term kernel, it appears so many times, sir, in different contexts. Does it have different
That
meaning?
different. I mean, relevant but different. Yes.
But it really बहुत डराता है sir ये word kernel actually. तो
it's the commonality everywhere you see it now. If you see the commonality, it is applying some, if it is doing some kind of transformation to the original data wherever you see the kernel. Even if you see in CNN, wherever you see this kernel term, it is a kind of, you can imagine like it's a kind of function that is doing some transformation on the input data. It means it is taking the input data and it is giving some output, that it is transforming the input to some other form.
Okay, sir. Thank you, sir.
Any other query here? Clear everything? Shall we move on?
Yes.
Not clear, you can ask queries, you can continue asking, no problem. Anything
Clear,
else
sir.
that you clear? Okay. So the next one, there is another way to deal with the multi-class classification, right? In the scikit-learn library, there is something called sklearn.multiclass, in which you can directly import one versus one classifier or one versus rest classifier. Like that, there are various methods. You can import them and pass the base method to this one versus one classifier or any other classifier. So the base method that we are taking here is the linear SVC, linear support vector classifier. Okay, so the same thing, iris dataset I am doing. This time I am loading it from the library directly. Split the dataset, call the model one versus classifier. You need to pass the base classifier for this linear SVC. Like this, any binary classifier you can pass as an input for this. So fit it for the training data, predict for the test data, and evaluate it. That's all. Okay. So like this, you can test here also. Okay. So that's all. So sklearn.multiclass, or directly you can use SVC by passing the decision
So
function.
we are getting some warning there.
There is some, because of the data set. Okay. You change the data set, it will. Sometimes we get this.
So
Okay.
we want to see the output once. Scroll it up.
There are some misclassifications because of the linear SVC.
So if we want to see through plot,
Similar to logistic regression model.
okay.
Okay, model dot coefficient u axis, model dot what is the other thing, intercept u axis, building them, but that is not possible for 4-dimensional or 5-dimensional data or more dimensions. If you have
Okay.
2-dimension, 3-dimension also possible. 2-dimension, then you can take the same code that we have demonstrated earlier. Yeah. All right. Any other query? Any other query? Clear today's session?
Yeah,
Yes, sir.
sir, data leak, what is data leak and something related to data? When we do normalization and preparing data for SVM, what are the procedures? Can you throw light on data leak?
Data leakage, if I understand this word correctly, see, this is some kind of unauthorized transmission of the data, or I felt it is something relevant to the security. Okay, data security, not to the machine learning. If I mean, to the best of my understanding. Okay, you can refer. If you think it is relevant to the machine learning, we'll discuss. Let me know. I'll go through it and discuss. That is relevant to the data security, sir. That data coming to the data preparation for SVM, it is like, I mean, whatever the whatever that we have done, no, in this, even in this program also, that is the kind of preparation that we do, not more than. So if you are talking about the data pre-processing, then that is different. Like if there are missing values, pre-process them. If there are some NaN values, or if there are some duplicate values, right, or something like that. So if the data is incomplete, or there are some noise in the data, So how to clean the data is different. But what you are talking is something different. Data leakage is relevant to the data security, not the analysis part of it. Okay. There may be machine learning applied for that data security. That's a different thing. But I mean, what is that you wanted to know exactly? I mean, from the context of SVM, I couldn't follow. If you can elaborate, that will help.
Actually, data leak in especially data preparation or pre-processing, there is a word for that. I mean,
No, the data
before,
leakage is something different. Maybe you're confusing between the words. Different. I mean, just check. I'm not sure about it. Just check.
okay.
But data security is something like something. I mean, some data is transmitted on. I mean, unauthorized transmission kind of thing, right? So then we call it as a data leakage. Okay, so data pre-processing is different from the data leakage. These two are not same. Data preparation or data pre-processing is different from the data leakage.
Sir, one last question from my end. So, when we do pre-processing, we have to do three things, which are very common. That scaling of the data, transforming the data, and normalizing the data. They are not one the same.
Yeah, not the same. What is your doubt? Then not only that, there are various other pre-processing techniques. Okay.
Yes.
That, as you said, they're most commonly applicable, and data cleaning also, like removal of the or I mean handling the missing values, or handling the noisy data, or transforming the data, like you said, the normalization or feature selection, or if you want to discretize, like there is a
Yes.
discretization.
With specific to these three things, scaling, transforming, and normalizing, we are trying to put the data in the range of 0 and 1. So
That is feature scaling.
That is feature scaling. Then normalizing also one putting things.
These two are used interchangeably. Normalization uses it for the regularization also. So it depends on the context that you're using that word.
Then data standardization is also putting data between 0 and 1.
Standardization is also normalization and standardization also they use interchangeably.
Okay.
See, madam, there are not only this, there are various ways of that pre-processing, like dimensionality reduction or feature selection is also one kind of pre-processing. Okay, or discretization of the attributes. Let's say that you have continuous data, you want to discretize it. That is also one kind of pre-processing. Or you say that feature scaling is also one kind of pre-processing. Or missing values, handling missing values, or handling the noisy data. All these are the various pre-processing techniques. It can be data cleaning, or it can be transformation, or it can be reduction, like that, various. In each one of this head, there are various other techniques. Okay, like if you see data, I mean various phases of it, facets of it. Okay, so like for example, if you take the data reduction, you can go for the feature selection, or you can go with the dimensional reduction, etc. Like that, there are various facets of it.
It depends upon what you want to do.
Yeah, exactly. Yeah. So how do you handle that all that pre-processing techniques? So many of the pre-processing techniques are there at a SQL learn pre-processing library. SQL learn pre-processing. And one more thing, that it's not only dimensional reduction always. Generating the features also, new features also comes under the pre-processing one. Like the transformation that you are doing, right? Like you might have seen that polynomial features in polynomial regression. That is
Yes, sir,
also
we
kind
have
of
seen.
pre-processing. Yeah. All right, sir. Parmeshwara, sir. Any other query? Anybody else?
Sir, no, sir. No, sir.
Okay.
Not today. We'll
Yeah, please go through it, sir. If you have any query, you can ask in the next class also.
Sir, could you suggest books on the data science, like for all ranges, for
Data science. One of the good book is
no,
statistical
you
learning.
sir, you show it all the author,
That
maybe
is
in
there
next
in the
class.
first day slide, sir. First day introductory slide is there, no? Textbooks cover pages are given in that last slide of that.
Okay.
Yeah, check. All right then. Shall we wind up or should we continue with the next topic?
No, sir, enough for today. It was good. Thank you, sir.
Okay. All right then. One more thing. Please stay 1 minute. Tomorrow I have meetings till 7 p.m. Okay. Do we have class at 7 p.m. or shall we skip tomorrow's? It's up to you. Either is okay with me. Either 7 p.m. It may take till 8:30. So 7 to 8:30, or shall we skip tomorrow's class and continue it on Saturday?
So it is up to you, sir.
Either is okay with me. I mean, I just want to make sure that you are comfortable with the classes timings also, because there are some changes, no, than what is promised. Unfortunately, that is happening because of the heavy schedule here in my institute. So meetings are coming up. I mean, the unscheduled meetings also coming up. So that's why this is happening. So just let me know. Okay. Or else I can post it in the WhatsApp group. Whichever option you like, you just like that option. Majority voting I will take. Okay. Fine. So thank you then. Happy learning. Good night.
Thank you, sir.